sun is roaring with flares and plasma clouds, but the trajectory of 3 Atlas doesn't move. Why? The proof is simple. Residuals, the small gap between prediction and reality. A real push wouldn't just tremble, it would shift, pushing the trajectory out of its uncertainty margin. To date, the gravity-only model holds. The only real push is outgassing, and we're not seeing the signal. The stability of 3 Atlas gives us time, first visual, solar eruptions flashing across the sun. Then a quiet graph. The tracking points of Tracy Atlas fit the predicted line. The contrast matters. In the next segment, we'll decipher those graphs, define the residuals and uncertainty margins, and show how teams decide if an orbit needs updating. No exaggeration, just the signals that would prove a real push, and why we don't see them yet. When the sun roars, but the trajectory doesn't move, solar storms seem noisy, orbit graphs seem quiet. So why do 3I Atlas points keep aligning as if nothing had happened? Here's the proof that matters. If the trajectory had changed, 2 things would appear. First, you'd see systematic residuals, and you'd see the uncertainty grow beyond the expected corridor. Residuals are the small gaps between where telescopes measure the object and where the math says it should be. Uncertainty is the forecast scatter, the envelope around the path that widens over time if the model lacks a force. Both are simple to track, and both are sensitive to small changes long before any big visual change in a sky chart. Solar activity has increased. Flares, coronal mass ejections, fast plasma clouds leaving the sun increased this week. However, the astrometric points, which are the precise positions recorded by observatories, continue falling on the predicted line within their normal scatter. That discrepancy is the clue. The sun is roaring, but the trajectory stays within its bounds. If a real force were acting, the points wouldn't just vibrate randomly, they'd shift consistently night after night. Let's define residuals in simple terms. You take an observation, subtract the predicted position from the model, and get a small offset. Do that across many nights. Random noise cancels, trends don't. Music, a trend leaning forward along the orbit, suggests a small push accelerating it. A backward trend means a small deceleration. A lateral trend hints at an inclination change. This is how orbit solvers diagnose additional forces without ever seeing the force itself. Now, the uncertainty margin. Think of it as a cone around the predicted trajectory. If your model captures real physics, that cone grows at a constant expected rate. If you've omitted a force, the cone must expand faster to keep including the new data. When that happens, analysts test new terms, readjust and observe if residuals decrease and the cone returns to normal. We've seen this before. Comet C212 S1 ISON developed strong activity approaching the sun. Its residuals indicated that gas jets were altering its motion before its disintegration, so teams added non-gravitational terms. Interstellar Comet 2 Ebersoft showed classic comet behavior, coma, dust, gas and orbit adjustments improved when those small push parameters were included. In both cases, residuals were the early warning. So what about today's solar bursts? The consensus opinion in orbital dynamics is straightforward. Gravity dominates. To change an interplanetary trajectory measurably, you need sustained push from outgassing or significant drag in a dense medium. Coronal mass ejections move outward, but their particles and photons scatter over an enormous area. The net push on a small body is minuscule compared to the sun's pull. Here's an order of magnitude anchor. In words, at Earth's distance, sunlight pressure on a 1m area is comparable to the weight of a few paper clips. Solar gravity on an object several hundred meters is more like a loaded truck pulling a long tow rope. A flare or coronal mass ejection can illuminate and briefly increase particle flux, but that only adds a whisper to a force already tiny. For minutes to hours, the average impulse barely pushes the trajectory, and that push is lost in normal measurement noise unless repeated in a consistent direction. Data to date says the simple model works. Residuals lie within expected scatter without a constant slope that would announce an extra push. The uncertainty margin isn't expanding faster than predicted. That means the current solution based only on gravity holds, and there's no need to add push terms just to seek a headline. If the sun isn't moving it, what would? The only serious competitor is outgassing, small jets acting like thrusters, plus a minor effect from light pressure. Let's test that next and expose how the first clues would look for TR and Atlas. The only real push, outgassing, light pressure, and what we'd see. If a change were coming, the data would whisper. First, you'd see a subtle, constant slope in time and position, small offsets aligning night after night instead of random scatter. For 3 and Atlas, that whisper would look like a slow drift along its trajectory in the sky, growing predictably as more observations accumulate. Here's the core idea in simple terms. Non-gravitational acceleration is a small push on a small body not due to gravity. The main cause is outgassing that occurs when sunlight heats surface ices, and these vent as jets. Orbit solvers describe this push with 3 parameters: A1, A2 and A3. A1 points radially outward from the Sun, A2 runs along the object's motion around the Sun, and A3 points normal to the orbital plane. Each captures a different way the push could tilt, accelerate, or decelerate the trajectory. There's a fair question on the table. Can interstellar visitors be compact and active? Oumuamua sparked debate because its trajectory showed a small non-gravitational signal but a clear visible coma. Could 3 and Atlas show a similar effect? The conservative answer starts with what we can detect. If 3 and Atlas were expelling sustainedly, astrometry would tilt in one direction and photometry would follow that tilt. Let's separate the mechanisms. Outgassing is a rocket-like effect produced by steam and dust jets. Solar radiation pressure is the push from sunlight itself. Outgassing depends on volatile content, surface geometry and rotation, and often leaves markers, a brightness following heating, gas lines in spectra, dust in the coma and asymmetric shapes. Radiation pressure depends on the area-mass ratio, so it stands out in very thin or small low-mass objects. The consensus opinion is that activity transmitted through the light curve and spectra is the clearest sign of outgassing. An alternative hypothesis is that a very smooth object with a high area-to-mass ratio could show light pressure effects without an obvious coma, but that requires specific properties and remains a hypothesis unless data supports it. Here's how the workflow works. Observers report precise positions to exchange centers. Analysts fit a gravity-only orbit. If residuals, those small differences, begin aligning in the same direction and increase over time, they test a non-gravitational model with A1, A2 and A3. A real physical effect should reduce residuals not just during one night, but across multiple nights and seasons. If the fit improves and stays stable, they keep the terms. If not, they return to gravity only. Music, what would we see in the data flow? A smooth brightness curve following heliocentric distance, not a single peak. Gas features in spectra like CNOH bands, plus dust dependence in reflectance. A coma not perfectly centered on the nucleus, and a tail favoring one side. In astrometry, the signal would be a growing residual along the trajectory to 2, meaning the object arrives slightly early or late relative to a gravity-only prediction, with displacement increasing roughly as time squared under constant push. Some argue that a fast solar storm could add a drag or push. The consensus is that any such impulse is brief and small and would be lost in measurement noise unless repeated with the same sign and geometry. Outgassing, however, can be sustained by sunlight and comes with those photometric and spectroscopic fingerprints. We have a useful comparison. Borisov behaved like a normal comet, showed gas and dust, and orbit adjustments improved with non-gravitational terms. Oumuamua had a small non-gravitational signal, but no clear coma, leading to alternative hypotheses about its physical nature and radiation pressure. Both cases underscore the same method. Follow residuals and look for matching physical pieces. For DRADI, Atlas, current positions and brightness don't require non-gravitational terms. The gravity-only model fits cleanly, so teams maintain the simplest solution while watching for any deviation. With the orbit staying stable, we can set windows for deep imaging, spectroscopy and time series photometry in the following days and weeks. Conclusion, here's the key. High solar drama doesn't equal orbital drama. 3 Atlas stays on a trajectory governed by gravity and measured positions confirm it. The residuals, the small differences between predicted and observed points show no constant slope and the forecast margin remains stable. Your move now is simple. Watch residuals, not eruptions. Follow upcoming orbit solutions from MPC and HPL and support observatories publishing new astrometry so adjustments stay accurate. That stability buys time, ensures pointing plans, deeper spectra and better light curves. If numbers change, you'll see it here with clear sources and proofs.